Hi, folks. This is Miss Gray, and this is our first podcast of Unit 9, The Nature of Gases, also known as Podcast 9.1. So, hopefully, you've got your notes out right now and you're ready to fill in all those blanks on your note taking worksheet. So, get that ready. If you don't have it out now, get it out, push pause on the podcast, and get your notes in front of you. Here we go. This is what we're going to work on today. We're going to try and figure out, oops, sorry, let me just get what I need. There we go. We're going to apply the kinetic theory of matter so that we can describe relationships between temperature, pressure, and the volume of gases. We'll also work on how to convert units from one unit of pressure to another. And then we're also going to look at the relationship between pressure and elevation. Before we go any further, I'd like you to consider a hot air balloon. So in this slide behind you, you see a picture of a hot air balloon. Think about, what does it take to get this thing up in the air? Hey, how about that circle? Great. A hot air balloon up into the air. This thing's huge. How does it get there? Well, we know there's particles of air inside. And what do we do to make the hot air balloon float? Hopefully all of you at home are saying, make it get hot. We turn on the burner, right? And as we turn on this fire down here, then that heats up the air inside. We're not adding air into it. It's not like blowing up a birthday party balloon. Can you just imagine puffing your cheeks to fill a balloon this size with air? That would be insane. But what really happens is that whatever air particles are already in there, they just get hot. And so they start to move around inside here with more and more velocity, with more and more energy. So as they move faster and faster and faster, they're going to collide with one another, and they're going to collide with the walls of their container. And that's going to create a big expansion of air. And as that volume expands and the balloon gets bigger and bigger and fills up more and more, then it's just going to take up a lot more space. And as air particles take up more space, that reduces the pressure on those particles. So the pressure inside the balloon is going to be less than the pressure outside the balloon, and the balloon can float. Pretty amazing, isn't it? And that's what we're going to be working on in this unit, is the nature of gases. How can we get such a huge thing up into the air? It's pretty cool. So let's see how that works. First of all, we've got to understand what we mean by kinetic molecular theory. You studied in middle school how kinetic energy and potential energy are related. So when we refer to kinetic energy, what we're talking about is energy due to motion. So as I fill in my blanks, you're going to be filling in your blanks as well, right, folks? Great. Remember that all matter consists of tiny particles, and they're constantly in motion. So if it's a solid, then that particle is just vibrating and shaking, but it's not really moving around much. It's trapped in a crystalline structure, and it only gets to shake. But if it's a liquid particle, then it gets to move around from one place to the other. And then gases move in random motion because they don't interact with other particles much at all. Once they collide, they bounce off and go somewhere else. And so gas particles don't stick together at all. Liquid particles are constantly sliding around, in, over, and through. So they are interacting pretty closely all the time, but gases are not. Once we add kinetic energy, that means that we're heating it up, right? Atoms and molecules move faster then, and the object expands. Because, more collisions take place, and they need more room to move. If we lose kinetic energy, on the other hand, then the atoms and molecules slow down, and the object is going to contract or get smaller. Of course, I mentioned before, adding or losing kinetic energy means that we've adjusted the temperature. When heat is added, that means we've added energy. If we have more kinetic energy, then we get more and more collisions. So what does that mean for matter? Well, in the lab tomorrow, you're going to get to see a demonstration of what exactly that means. When we heat something up, what's going to happen to it? We'll find out. And let's get pressure specifically. If gas particles bump into one another, we don't really notice that. We do notice it though when they collide with some container. So pressure is defined as the force per area of an object. So if we put gas inside a container, then it's going to collide with the walls of the container. So this force is caused by the collision of gas particles. The more collisions there are, the greater the force. The greater the force, the greater the pressure. In a vacuum, we're referring to an empty space where there are no particles. And if there's no particles, there will be no collisions. And if there's no collisions, then there's no pressure. We measure pressure in such a way that compares it to the pressure of the Earth's atmosphere. So we call it atmospheric pressure. It results from the collisions of particles in the air that is surrounding the Earth. So if we have the Earth as an object and here's its center of mass, then the farther away you get from its center of mass, the less gravity can influence those particles out here. So the closer you are to Earth's surface, the the more gravity can pull those particles in towards its center of mass. But when they're way out here, it's going to be a lot weaker of an effect. So there's a lot more particles of air here near the surface of the Earth than there would be farther away, way out here. The pressure that's exerted on the Earth by the layer around it is called atmospheric pressure. When you're at high elevations, you're farther away from the surface of the Earth, so there's fewer air particles. Where there are fewer particles, there will be a lower pressure, of course. We measure this kind of pressure with a barometer. Here's how a barometer works. The particles in the air push down on the surface of the mercury liquid in this container. As they press down on this container, then we're going to see the mercury get pushed up inside this narrow glass tube. The higher the mercury rises, the more the air is pressing down on it. So that makes sense. We need to measure how high the mercury goes. So one of our common units of measure is called millimeters of mercury. How high is the mercury inside this barometer? But in the scientific units, the SI units for pressure, we're going to call those kilopascals. And you already know at sea level that air pressure is 101.3 kilopascals. We call that standard pressure. 101.3 kilopascals corresponds to 29.2 inches of mercury. Inches, of course, is not a metric unit, so we don't use that one very often. Or 760 millimeters of mercury. So a barometer is a handy device to measure air pressure just by letting air do what it does, collide with other particles. In fact, air is colliding with you, too, at a rate of about 1 billion times a second. It's a good thing air doesn't have much mass, or that might not feel very good. So what do we mean by vapor pressure then? How is that related to atmospheric pressure? Here's our new term, vapor pressure. This is simply the force that's exerted just above the surface of a liquid by particles that have evaporated from that liquid. Thus, it's called vapor pressure. So there's a place in your notes where you can draw this picture. It's meant to be a beaker. Sorry. Let's try this again. If I can get the pen to do what I want it to do, then this picture might turn out better. Yeah, eraser. That's all right. You guys have always been better artists than me anyway, so I have no use in pretending that I am a good artist. But I will try and clean this up a little bit just so you can follow along better. All right, so we have a container with a liquid in it, and there's particles inside our container that are in the liquid phase. And some of those particles, when they bump into one another, will collide with enough energy that it actually gets knocked entirely out of the liquid phase completely. So it goes from being a liquid particle to now, hey, it's up here. Well, it's not stuck to the other liquid particles anymore, so that particle is a gas or a vapor. And the more particles there are, the higher the vapor pressure will be. So if there's more particles above the surface of the liquid, then we'll have more particles that go from the liquid phase to the gas phase and a higher vapor pressure. If we raise the temperature, then we can get more of the liquid particles to collide with sufficient energy to turn into a gas. If we lower the temperature, then of course we're going to lower the vapor pressure. That's just how that works. Fewer collisions, less energy, fewer particles in the vapor phase. All right, well, let's measure this then. How do we measure this? Common units are pascals, but we commonly use kilopascals, which is technically the SI unit of pressure, kilopascals, which is 1,000 pascals. 1 atmosphere is what describes the entire Earth's atmosphere pushing down on you. So this would be like the pressure of the air that you would feel at sea level. Of course, at standard temperature of 0 degrees Celsius. So this is called pressure at sea level. Some of you just had a lovely spring break where you got to go to the beach and stand at sea level. And by the way, I am totally jealous because I didn't go to the beach for my spring break. But those of you who did know that the air kind of feels different there. Well, one reason is the pressure is different there than it is in Colorado, especially in Falcon, Colorado, because we're pretty high up. Another unit for measuring air pressure is called torr, which is equal to millimeters of mercury. Torr is just another way of saying millimeters of mercury, because mmHg is just kind of awkward. So here's our unit conversions. 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 760 torr, because remember I just said they are the same. See, 760, 760, they're the same. And you already knew what this one was, STP 101.3 kPa. All right, well, let's see an example of how to do this. It always helps for us to work an example. And gosh, that's kind of in the way. Oh, we'll work it through anyway. Suppose that we start with 450 kilopascals, and we'd like to convert this to atmospheres. Since I have kilopascals here on the top, then we know in the next step of our t-table, we've got to put kilopascals on the bottom. But what number do we assign to it? When we're doing conversions, it's going to be our conversion factors. It's this number, 101.3 kPas. And we're trying to change it to atmospheres first, and so that's what goes on top. So let me show you what this looks like. Here, I'll get rid of this writing so it's not in the way. 101.3 goes on the bottom, 1 atmosphere goes on the top, and the result, when we take 450 divided by 101.3, the result is 4.4 atmospheres. I'd like to show you that on the calculator so you can see what numbers I got. So we started with, let's scoot this over. Oh, turn on your calculator. Don't you hate it when you go through all your steps in the calculator and it wasn't even on and you pushed all those buttons for nothing? 450 divided by 101. Oops, I pushed 111. 450 divided by 101.3. And then I get all of these numbers. And of course you already know, not all of these numbers are significant. We started with 2 sig figs, so the most I can keep is 2 sig figs here. So the 4 here is not big enough to make a difference. It's just 4.4 kPas. Let's try another problem. Now we need to change 450 kPas to millimeters of mercury. So we'll put kPas on the bottom again, 101.3, And then look back up here in your conversions for millimeters of mercury. Here it is. That's what we want to turn it into, so that's what's going to go on the top over here. 760 millimeters of mercury. When we do this math in the calculator, it's multiplication because we take the top times the top and the bottom times the bottom, then we divide the top by the bottom. All right, so let's do 450 times 760. And then we don't need to divide by the bottom. Oh, we sure do, because I thought it was 1, but it is not. It is 101.3. So we divide by the bottom, and that's not the right answer. I knew it. Try again. 450 times 760. Now this time, I want you to push enter. And then divide by 101.3. Oh, that was the right answer. Looky there. You know why? Because this is a big number. 101.3 is standard pressure, right? So we need something that's way bigger. 450 is way bigger, 4 times bigger, in fact. And so we need a pretty big number here. Sorry for confusing you. Let's look at sig figs. 2 sig figs are allowed. So in this number, I have to stop after 3376, right here. This number, this 7 is bigger than 5, so that's going to make a big enough difference that I need to round up. So where I have 3376, let's change that so that it says 3.4 times 10 to the third power. Why 10 to the third? Because to get to this spot right here, I have to move the decimal over 3 times. And of course that's millimeters of mercury. And once we get our answer, what do you do with that? You put a box around it. Why? That's right, because that's the way I like it. Good. Oh, get rid of the writing. Oh, wrong one. There's the button I wanted. Hey, guess what? That's it. That's the end of podcast 9.1. So here's what I need you to do in class tomorrow. When you come to my class, we're not going to do this worksheet. We're just going to work through these problems. Let's see, there's 1, 2, 3, 4, 5, 6 problems to work through. We'll go over your Unit 8 test, and your parents will need to sign that test analysis. And then we'll also have a demonstration, not just one, but many demos that help you understand how the kinetic molecular theory works and other properties of gases that are going to be important for you to understand this unit on the nature of gases. That's all there is, folks, for this podcast. I hope that you have enjoyed this and that you've been able to follow along. Like I said before, if something's working well for you, let me know. And if there's something that's not working for you, let me know so that we can fix it. Have a good night. Bye-bye.